Hello, everyone. My name is Eric Greenwood. I'm an assistant professor in the Aerospace Engineering Department here at Penn State. I've been here for about a year. Prior to that, I was at the NASA Langley Research Center. Today, I wanted to talk to you a bit about some of my experiences applying machine learning and parameter identification techniques in order to develop useful noise models for helicopters. A lot of this work was done during my time at NASA Langley, and particularly using a lot of the data that we collected doing acoustic flight tests of helicopters. So helicopter noise is becoming an increasingly important issue. And communities are concerned about the operations of rotorcraft in their areas because of the annoyance caused by helicopter operations. And fortunately, we've had some pretty good experience mitigating that noise by adjusting the way helicopters fly. Um, so over here on the right, this is a plot that shows what we call sometimes a fried egg plot. This is basically a diagram that's intended to show a helicopter pilot. The areas of the helicopter that is operating envelope. So this terms of airspeed and rate of sink that cause objectionable levels of noise. So as you can see, at a particular moderate sink rate and moderate airspeed, we have a maximum of noise. And the idea here is that the pilot could use this sort of guidance in order to design, say, an approach to a helipad that avoids that noisy region. For instance, maybe by descending steeply at high speed and then decelerating and then reducing to a lower airspeed and coming down for a landing. And this can be really effective because, as this diagram shows, the noise radiation of the vehicle is very sensitive on its flight condition. Now, the acoustic characteristics, unfortunately for us, in terms of giving pilots guidance, vary quite a bit depending on the type of vehicle the pilot's flying, but also how that vehicle is configured. What's the gross weight? Are you carrying any external stores that change the drag? The ambient conditions, so air temperature and density, and what kind of operations you're performing. So this chart here on the bottom is just a notional diagram, and it shows some of the things we've discovered in recent research about how changes in the altitude or whether you're doing a turn or the vehicle weighs more can influence where this fried egg plot actually appears in such a way that a diagram that you'd really planned based on some notional steady flight data that was collected at one location originally may be invalid for your specific environment. And we're still struggling to produce accurate first principles predictions. So we can, and we've had some good recent progress in terms of prediction of helicopter noise, but it's still very time consuming, both in terms of effort to put together those models, and then also in terms of the computational time it produces to, requires to predict the noise. So, we're not at the point where these are useful tools for helicopter operators in order to figure out how they should fly in their specific circumstance. So what we really need here are ways to get these operators some timely information, which is specific to the type of mission and the weather conditions and their vertiport that they're flying into that day. Now, the primary cause for a lot of this variation in noise is a source that we call Blade-Vortex interaction. So it's worth talking a little bit about the physics behind that. So this is basically a noise source that occurs when the tip vortices that are shed by the helicopter rotor blades pass nearby those blades. So this typically happens during a descending flight condition because that's when the wake convects into the rotor, and what we call the mist distance between the vortex and the blade grows small. When that happens, this vortex induces a velocity onto the airfoil of the rotor blade, and this causes a very quick change in the angle of attack. And because and that causes a corresponding change in the air loads, and because the resulting acoustic pressures are really a function of the time rate of change of the blade surface pressures, that generates an impulsive source of noise, which is highly objectionable, both because of the frequency range in which it occurs and because of its magnitude. And again, because this is dependent on the relative position of the wake and the rotor blades, it's very sensitive to the operating conditions. That's what gives us that Friedberg plots that was shown on the previous chart. And it's also extremely difficult to accurately compute, because we need to, resolve the properties of this vortex over quite a long period of time after it's shed from the rotor blade until it interacts with the rotor blade tip again. During my time at NASA, we collected noise data incidentally across a number of helicopter acoustic flight tests for a fairly wide range of helicopters. So we collected noise data, at the time of this for 10 civil helicopters. We've actually, since then, there are 14 helicopters in the database over a wide range of steady flight conditions. So overall, over this range of helicopters, noise data were collected for over 1,500 different individual steady flight conditions. And this included, measurements that were taken at sea level, so this like Robinson R-66s in Florida at Eglin Air Force Base, all the way to, say, some measurements that were collected at pretty high altitude. So one of these photos of the Airbus AS350 was collected at a elevation of 7,000 foot up in the Sierra Nevada mountains. So the density, altitude, and the air temperature, and all the ambient conditions cover a pretty varied range over this set of data. And for each of these steady flight conditions, the helicopter passed over an array of microphones, and we can depropagate the data from those microphones. So essentially remove the effects of spherical spreading and atmospheric absorption, and then relate them to the emission angle around some fixed distance, and therefore form a sphere of noise that describes the levels as a function of frequency, direction, and the operating condition of that vehicle. So overall, this is a very expansive data. I don't think there's another set of data, but I don't think there's something comparable out there. But it's still quite small compared to sort of a lot of big data applications where instead of looking at maybe 1,000 points, we have millions. Nonetheless, can you use these data in some way, since we had it, in order to inform a useful model that could provide helicopter operators with noise abatement information? So the first step here is really to figure out how we're going to classify this data, to produce something like that Friedberg chart, where we can figure out what operating conditions are noisy and which ones aren't. So we're going to take these noise spheres that we have, and then we'll propagate them back to the ground for a kind of a reference altitude and condition. So over here on the left is a plot that shows a stereographic projection. So we're looking down into one of these noise spheres, and this is for a descending flight condition of the Bell 430. And we can see over here on the right, upper right of this plot, we're radiating quite a bit of Blade-Vortex interaction noise forward and towards the advancing side of the helicopter. So we're going to take each one of these points and then propagate to the ground and integrate that into a noise level, which we then adjust for duration. As the helicopter travels faster, we can say it's going to fly over any given observer for a shorter period of time, and therefore something like the sound exposure level would be reduced, and so we'll account for that too. And then we'll put these points on this map of the helicopter's operating envelope, so in terms of, say, rate of climb or sink, and the speed. And each one of these dots here now represents one of those points. And I've then taken and interpolated this metric that we came up with between all of these points on this contour. So you can get a sense of this noisy region where the red values are for this particular helicopter. And then for each of these points, if it's in the upper 30% of the range of noise levels we found over the entire space of operating conditions we collected, we're going to call that one a noisy point, and those ones are marked by red. And that's just a heuristic, but kind of from a I know it when I see it sort of perspective, we see it matches fairly well with kind of the loud region of this operating envelope, and was generally true across a range of helicopters. And when we look across a range of helicopters, what we see is, just as I indicated before, where the noisy operating condition or noisy area of the operating envelope occurs varies quite a lot between different helicopter types. So here we're comparing that Bell 430 on the right to MD 902 in the middle, and Robinson R44 on the left. And we can see, you know, for the R44, the operating envelope, you know, that noisy region occurs at low speeds and relatively shallow sync rates. Whereas for something like the Bell 43, we're at higher speeds and higher sync rates. And this is all, you know, a function of the vehicle's weight, drag, you know, size, and parameters like that. So as we can see, you know, and if you look across the whole range of 12 vehicles, there's really no clear pattern between where this operating envelope will occur. So we want to find a way to help us, because we don't have that much data, and collapse this data set into something where, you know, maybe we can draw a box around it that surrounds the data that are noisy across all vehicles versus those that aren't. And a good starting point, like any engineer should do, is to look at what are the non-dimensional parameters that really govern the physics of my noise generation. And you know, a lot of aerodynamic theory and experimental tests, both for aerodynamics and for acoustics, have shown that the operating state of the main rotor of a helicopter is really a function of some set of 4 non-dimensional parameters. And I picked one set of 4 that's consistent here. First, the angle of attack of the main rotor. So if we view the entire rotor tip path plane, kind of like an airplane wing, the angle that the flow, you know, the oncoming flow makes with respect to that angle of attack. And that's, of course, related to the sync rate of the vehicle, as well as its drag. And that controls, to some extent, the separation between the rotor blades and these tip vortices in the vertical axis. The weight coefficient, and this is just a non-dimensionalization, essentially, of the rotor thrust for steady flight. And that controls how strong these trailed vortices are. The hover tip Mach number, and then the advance ratio. The advance ratio being a non-dimensionalization of the forward speed with respect to the tip speed. So these two in combination basically determine the epicycloidal geometry of the wake, so the top view that we have this rotor wake. And that determines the interaction geometry between the blades and the vortices, which is also important in determining the magnitude, as well as the directionality of Blade-Vortex interaction noise. So when we take a look at the data as a function of these parameters, we find that the data actually collapses pretty well. So this is a little video. It shows all of those 1,500 points. And here, the ones that are marked in red are those points that are classified as noisy, and the ones that are black, those that are not noisy. And here, because I can't show you a 4-dimensional plot, I just picked 3 parameters: the weight coefficient, angle of attack, and advance ratio. And now we can at least see that, you know, you can kind of imagine how I might be able to draw some kind of envelope around that cluster of red points that determines the noisy region across these different vehicles. So after we've done that, we want to further condition the data before we start to apply some you know, empirical model building techniques to it. And we're going to do this in a few ways. So this shows just the example for one vehicle. This is an MD 902. And we've plotted the data, again, noisy in red and not noisy in black, angle of attack now versus advance ratio, so that non-dimensional form. First, what we're going to do is we know that as the angle of attack increases farther and farther beyond what we normally fly, eventually the Blade-Vortex interaction noise is going to start to decay, because the rotor wake will at a very steep rate of descent be above the rotor, and so we won't be generating a lot of noise. So we don't have this measured data a lot of the time. So what we're going to do is add it synthetically. We can add some points at a very high angle of attack, kind of knowing that you know, there's not going to be BVI noise there, and that'll help sort of close this noisy region, so it doesn't exist, or sort of it doesn't seem open-ended for a particular helicopter, a particular angle of attack. Then the next thing we have to look at is, you know, based on our definition of what's noisy and what isn't, we typically have something on the order of 7 times as many not noisy points as we have noisy data points. And a lot of machine learning techniques in particular are susceptible to bias being introduced toward the majority of points. So we really want to balance out the number of points that we have. One way you might typically do that is to essentially decimate your data and then remove data from conditions where you have too many. Unfortunately, we don't have a lot of data to spare. So what I've applied here is a technique called a synthetic minority oversampling technique. And this adds in a quasi-random fashion some additional synthetic points, these are these blue ones, in kind of the region of the noisy points in order to oversample and bring those up to the same number of points as we have the non-noisy ones and give us a balanced set of data. So we can go and apply our algorithms, and I'm not going to go into all the details here, but these days, in this case, I used scikit-learn. It's relatively easy to interchange different machine learning algorithms and see which ones perform fairly well and which ones don't. And I applied a number of different models. And the nice thing is, because these are kind of probabilistic models in general, I can plot maps that show the likelihood of a point being noisy given this particular space. So this is for a model that was built over all helicopters using like a five-fold cross-validation technique. So that's using 80% of the data for all in that data set with all of the data for one particular helicopter removed completely. Just to give a fair comparison of how well we would do generating a model for a vehicle we've never seen before. And most of the methods give me pretty similar results. Probably the best accuracy was with the multilayer Perceptron. So that's like a typical neural network-like approach. We also had a random forest technique, which had pretty good accuracy, but you can see gives a pretty odd shape contour because it's based on a decision tree, essentially. However, the random forest technique does have one benefit in that it's a kind of a white box model. So we can actually figure out which parameters were most important to the random forest model in determining whether a particular condition is noisy or not noisy. And one interesting thing that comes out of this is that pretty reliably for every helicopter, the angle of attack was the most important parameter and the advance ratio the second most. And the other parameters were significantly less important. Here I'm just going to show, for the one multilayer Perceptron, how well it did on a selection of these models. And there's a paper you can see where we have results for all 12 helicopters. And in general, this region that's shown in a hashed shaded area is the region that the model identifies as noisy for a helicopter it hasn't seen before. And it does a pretty good job identifying what seems to be the noisiest region of that envelope. So this is a pretty successful approach in generalizing our data. If we do need more data, there's another approach I developed called fundamental Rotorcraft acoustic modeling from experiments, or FRAME. And the general idea here is that we could take some experimental data, again, non-dimensionalize it, and then use that to inform some kind of model that's based on physics using a parameter identification technique, which we can then apply to generalize that data. So once we've calibrated this relatively low order semi-analytical model, we can now make predictions, say, to see what happens to Blade-Vortex interaction noise as we take that helicopter from sea level, where we maybe measure that data, to different altitudes. We can see, for instance, in this chart here, the predicted behavior is quite nonlinear, and it's going to be very difficult to accurately estimate if you only had data at one operating condition. So the core of this model is this analytical model, which is non-dimensional, and it really represents, to first order, the governing physics of the Blade-Vortex interaction noise problem. So there's models for vehicle trim, blade flapping, dynamics, acoustic propagation, and the wake itself, which is going to give us our Blade-Vortex interaction noise. So to give you an example for the wake, here's the ordinary differential equation that represents the convection of the wake from the rotor blades. And we have aspects in there for the rotation of the vehicle, for the velocity of the vehicle, and then for the flow that's induced by the rotor on the vortices. And inside of this model, we've identified in these square boxes what we call dependent parameters. And they're really parameters that would be typically empirical in this semi-analytical model. But we're going to calibrate them to measure data for a particular set of those non-dimensional governing parameters. Right? And those non-dimensional governing parameters also appear directly in the model, things like the thrust coefficient or weight coefficient, the wake skew ratio, chi, which is related to the angle of attack, and the advance ratio, mu. So then we will conduct our parameter identification process on some measured flight test data. We'll first isolate out, the characteristic rotor noise pulse that's shown in the lower left, and then we'll make a prediction with our model, and we'll then use a parameter identification process, essentially an optimization technique, in order to adjust the empirical parameters of that model until the output, the simulated output of that model, matches the isolated rotor pulse that we pulled out from our measured data for that particular flight condition. And we're going to do this on the basis of an error norm in the time domain between these two pulses. So even though we might be interested in is just the overall sound pressure level, by including this error norm, we're actually tracking the phase differences between these two harmonic pulses. And hopefully, if we can get that right, that means that the underlying physics in our model have been calibrated correctly. And just to give you an example of this in application, here's a set of noise spheres. So for that AS350 helicopter that I showed before, we collected data actually at sea level for that vehicle for Blade-Vortex interaction noise on the sphere. And you can see this one BVI hotspot in the diagram in the lower left. And then we use that data to calibrate the frame model. And over here on the right, you can see the calibrated data. You can see we have the magnitude and directivity of that hotspot quite accurately captured. At other directions, the noise levels fall off quicker in the model because we aren't modeling things like broadband noise or the tail rotor in this particular example. And then we also took some measured data at 7,000 foot altitude for this vehicle. And what we can see is that the directivity of that BVI pulse changes and the magnitude has decreased. And indeed, the frame model calibrated to sea level data accurately represents both of those changes in directivity and magnitude, because at least the first order accurate physics are embedded in this model. And having a model like this that gives us quite a bit of detail, we can now apply it relatively quickly compared to another model, in fact, in real time. So this is an example from a noise training aid that I worked on with Anna Trujillo and Dan Hill at NASA Langley. And this can show a helicopter pilot the footprint of the vehicle in real time, specific to their particular set of operating conditions, configuration of the helicopter, and weather, in order to help inform helicopter operations to keep that noisy footprint outside of populated areas as much as possible. So with that said, I just want to wrap things up and conclude. So I think, when we're doing these aeroacoustics problems, particularly with real aircraft, we never have enough data, both in terms of data points. We're never going to get the millions of new data points a day that something like Facebook gets when they apply their big data problem, but also in terms of breadth, right? It's easy for us to miss configurations or operating conditions that happen in real life pretty regularly in our set of data. And that kind of makes it hopeless for a purely empirical approach really to extrapolate out to those changes where things can happen quite differently. So we really need to use our subject matter expertise in order to imbue these models with as much of our physical insights as we can. So we can apply non-dimensionalization in order to try to collapse the data we do and make it into a simpler problem. Condition that data in order to emphasize those features that we know are important to the end result. Where possible, right, actually embed those the physical insights as models in order to improve that generalization. So, at least our physics can be extrapolated beyond where we are, and then we're hopefully then leaving things that don't vary that much up to the model to calibrate. And lastly, we want to be able to extract as much information as we possibly can from the data that we do have. So even if our model output that we care about is a weighted sound pressure level, we might want to tune that model on things like frequency or, like I did, the pressure time history signal, just to make sure that the physics that we are representing in our model are correct even if we're not going to use that end result. And, overall, I think a lot of these things have worked out quite well, but the big challenge that remains is figuring out how to turn these models into something that can be used, in order to reduce noise or help designers or something like that. We want people not to have to be experts in machine learning and aeroacoustics in order to take advantage of our results. You're trying to find new ways to convey this increasingly complicated set of information, in our case to helicopter pilots, is still kind of the big challenge. So thank you very much for your time, and I look forward to talking to the panel. Take care. Bye.